Okay, what I'm going to do is just start off with a problem that's going to be a one-sample t-test. And what it should do is focus on how close to the same this is as a problem we've already worked. Of course, there will be a couple of differences, and we want to get those as well. So what we have here is a random sample of 49. So n is equal to 49. The sample mean is 31.7. With a sample standard deviation of 0.70. By the way, that's the big difference right here. This is how we know we're doing a t-test, because it has sample standard deviation. If you have sample standard deviation, you're doing a t-test or a t-interval. I'm going to go ahead and calculate then the standard error, but now it's SX bar because we have sample standard deviation. S divided by the square root of n is 0.7 divided by the square root of 49, and I believe that's going to be 0.1. I'm going to use my calculator. Can't even get that going right here. Yes, 0.1. By the way, it says then, can we conclude that the population mean is less than 32? And that ought to all seem pretty, I guess, commonplace by now. It's just like the thing we did, except for we have sample standard deviation. The symbol for that is C. So our standard error is going to be SX bar. So we're going to reject HO if, now since we have sample standard deviation, it's t-test less than minus. It's the same rule as before. Look at your research hypothesis and then do whatever the sign there is. If it's less than, this is less than minus. Look at the research hypothesis. So now what you need is you need a copy of the t-table. This is the green table that I handed out. It's in the green tables that I handed out. Looks like it's on about maybe starting on the back of the page 4, and it's going to be there for that and the next one. At any rate, it's the one that says t-table. See how I hid that on here? We're looking for the t distribution, so we go to the t-table. Now, if you look at the top of the table, you will see something that looks similar to what I gave you in the previous test. That is, at the top you have a confidence level, and across that row you have 99, 98, 95, and 90. Then you have so those are confidence levels for confidence intervals. Then you have 1 and 2 tail tests, and those numbers up there, the 0.5, the 0.1, and all of that, those are alpha levels or level of significance. So in this particular case, we have a 5% level of significance. So that's alpha is equal to 0.01. It's a one-tailed test. And then the degrees of freedom, it's going to equal to n minus 1. In this case, we have n is 49 minus 1, that's 48. So if you go first, I would recommend along the top of the table, one-tailed test 0.5. We see we're going to be in the first column there. And then just go down to degrees of freedom, and where it's 48 there, the cutoff is 1.677. So when you have a sample standard deviation, you have a t-test, correct for degrees of freedom. That's all I've done. Then I'm going to compute the t-test, and that's going to equal to the statistic minus the hypothesized parameter over the standard error. And let's see, we had 31.7 minus 32 over 0.1. That's going to be minus 3. Which is less than minus 1.677. So we reject HO and conclude that mu is less than 32. Now, while I have you here, what I want you to do is get your statistical calculator out, and you will absolutely need a statistical calculator on this test. Hopefully you have one already. If you don't, it's time to quit putting it off and bite the bullet on this. One of the reasons for that is that if we were going to compute p-values for the t-distribution, we would have to have a separate z-table-like thing for every line of the t-table. We're not going to do that. We are going to let calculators and computers calculate p-values for us. For this test, we'll just be using calculators. After that, after spring break, we'll start getting more into the use of computers to calculate statistics and p-values and t-tests and all that kind of thing. So anyway, you got your calculator out, hit your stat key, and go over to tests. Option 2 is the t-test. So for mu 0, that's from our hypothesis there, that's 32. For x bar, that's 31.7. I assume you're entering the numbers along with me here on your calculator. The standard deviation, remember this is the standard deviation, not the standard error, so it's the 0.7. And the sample size was 49. And then this last thing there, or the mu, last line before the calculate, all that needs to have the same sign as your research hypothesis. So make sure that says less than. And then hit calculate. And you will see there that the t is minus 3. And you will also see that the p-value, I'm going to write this right here, p-value is equal to 0.002. And that's the only way we will calculate the p-value when we have a t-distribution. So to draw the sampling distribution of that, it's going to be really similar to what we had previously. HO was that we had 32 here. We actually found a sample mean of 31.7. And this area out here is the p-value, 0.002. The reason it's down here because we have a one-tailed lower. So remember, we're going to reject HO if the p-value is less than 0.05. And let's see, we're going to reject if p-value less than 0.05. 0.002 is less than 0.05, so you reject HO. Conclude that the population mean is less than 32. If we wanted to go further, and we do, we can go ahead and have the same interpretation of this p-value that we did. I'm looking at part D now, that we did on the previous exam. Same exact interpretation, or at least method. If mu is equal to 32, if the population min is equal to 32, then there is a 0.002 or very small chance of observing a sample mean less than or equal to 31.7. By the way, we did get one of 31.7. Therefore, we're pretty sure that mu's not 32 because there's almost no chance that we would get this if the population mean were 32. If you haven't gotten the reasoning down on that yet, please go back and review and make sure you get that reasoning of the p-value ironed out. Okay, on part E, we're going to do the confidence interval. And when it says the theoretical thing, just go back to the previous test. It's the same thing where we draw, if you sample repeatedly, what proportion of the intervals would include the real population mean. Remember, the interval, that's really independent of any problem when we get to the theoretical idea of a confidence interval. So you can look on the last test or anything we've done before. It's the proportion of intervals. If we kept sampling, it's the proportion of intervals that would include the real population parameter, in this case, the real population mean. But anyway, I'm going to see if I can squeeze in the confidence interval here. It's a little tight. But it's just going to be x bar plus or minus t times sx bar. Our x bar was 31.7. For 90% confident, we're going to still get that 1.677 times then the standard error, which was 0.1. And so all we have to do is do a little multiplying and subtracting and adding and all of that. 31.7 minus 1.677 times 0.1. That's 31.53 about. And then do the same thing, except for this time add. And I got 31.87. So this is one of those intervals that we might have gotten, 95% of which would include the real population mean, 5% of which would not. But if we wanted to look at this interval and say, is it plausible that the mean could be 32? We would say no, the whole thing is less than 32, so we would be confident that the population mean is less than 32, again, because the whole interval is less than 32. We're also confident it's greater than 31, but we're not confident that it's greater than 31.5 because that's in the interval. So the main conclusion is that the population mean, we're pretty confident the population mean is less than 32. The sample size large enough, it's 49. It's large enough if there are no outliers in the population. Same rules as we used on the previous exam for the one sample. For the one sample z-test. Sorry, I lost my concentration there for a second.